All right, good evening once again. So here we are again for, this is going to be part 3 of lecture 7 of ENGR 2302 Engineering Dynamics. So I covered the basic theory of collisions in 1 and 2 dimensions, or oblique and let's say so central and direct, I should say. Actually, let me back up and say, I don't want to get a little sidetracked there. So direct central and oblique central impact. But I would like to move on and say, and discuss the, and work through a few example problems, I should say. Okay. So all I'm going to do in this portion of the lecture is cover a few example problems. So let's do example 1. Example 1. So I'm going to have this given. This is all going to be solved for in terms of V. So let's see here. I'm going to have a wall and a ball striking this wall. So I have a ball and the ball will strike the wall. And the ball comes in at a velocity of, well, I'll just say V. I'm going to do all of this in terms of simply V. Simply V here, velocity V, and it's going to follow a path something like this. It will ricochet, and I know from basic physics that if there's only one object striking a horizontal wall, it will rebound with the same angle. Anyway, then let's say that the angle here, the angle of impact, is 30 degrees here. So it forms an angle of 30 degrees. And actually, well, I don't want to say that that will rebound at the same angle. So I don't want to say that. It may not. So let's resolve this and see how this will end up. So actually, in this case, it may not end up with that. That would be for a perfectly elastic collision. I don't necessarily want to say that. That would be, say, a bouncy ball, or maybe even something like a good example would be light, a particle of light, a photon striking the surface and reflecting off a mirror or something. Okay, and also I will be told that the coefficient of restitution is 0.90. And I wish to find the magnitude and direction and I will label this as given here. And I wish to find the magnitude and direction of the reflected ball. In terms of V. So in terms of V. In terms of V. All right, so let's get this here. Now, and also this is a frictionless surface here. Frictionless vertical surface. All right, okay. So, I will also, my first step, though, will be to break this down into step 1 here. I want to break the motion into vertical, or actually not vertical, normal and tangential components relative to the wall. And tangential components relative to the wall. Although these could also be considered vertical and horizontal in this case. I should say break the ball velocity into normal and tangential components. So basically, let me draw this out here. The ball coming in will have a here. And I could do this in vertical and horizontal. However, I don't want to necessarily do that because I want to get in the habit of realizing that a lot of our components break down in terms of normal and tangential planes. So I could actually, in this case, normal tangential will actually be vertical and horizontal, but, or actually vice versa. But I do want to just sort of get in the habit of doing this. So this is our velocity initial, and I can just say v, our initial velocity, and this will have components, v tangential, so tangent to the surface here, and then component vn, v normal. And then this thing will rebound, and after it rebounds, the ball will be over here somewhere, and it will have components also tangential and vertical and normal. It will have components, actually let me use the same color. It will have components vt prime and vn prime. I don't know the exact magnitudes of these, but I can go ahead and assume that the normal component will be going to the left and the vertical and the tangential component will be going upward. So let's go ahead and do this. Okay, so resolving is let's actually get the initial components. So this is actually not bad. This is just basic vector algebra. This is just trigonometry. So Vn here is going to be v cosine 30 degrees is equal to 0.866v, 0.866v, and v tangential is going to be v sine of 30 degrees. 30 degrees equals 0.500v. And I can also, so step 2, so that's, I have now broken down the initial velocity into tangential and normal components. So step 2, realize that the normal component will be conserved. So in most collisions that we're going to be dealing with here, the normal component is going to be conserved. Is conserved. So, in other words, this is a frictionless wall. So what do I mean by this? The normal component is going to be conserved. So in other words, it's going to be, the tangential component is going to be conserved, sorry. The normal component will not be conserved. The tangential component will be conserved. Sorry about that. The normal, so the tangential component is conserved. And the reason for that is this is a frictionless wall. So it can exert a force in the x direction, but it cannot exert a force in the y direction. It is a frictionless wall. So there can be a horizontal exchange or a normal exchange of momentum between the wall here and the ball, but there can't be any tangential exchange. It's going to simply slide off. So from this, I can say that Vt prime equals Vt, or will be simply equal to 0.500 times V. And then step 3, I am going to apply the coefficient of restitution. The coefficient of restitution let's see, relation. Now, at first you might see, if you're looking at the formula for coefficient of restitution, you might say, wait a minute, how are we going to do this? Okay, so if I go back to where I defined the coefficient of restitution, I had this b here. So how in the world is that going to work? Well, in this case, we're going to treat the wall as an immovable object. So I will say, apply the coefficient of restitution relationship with 0 wall velocity. With 0 wall velocity. So in other words, 0 minus Vn, we're doing this in the normal direction, so 0 minus Vn prime equals E times Vn minus 0. So that will go away. And so then simply Vn prime, the final component of the final normal component of the final velocity, is going to be equal to 0.9 times Vn, or just negative 0.9 times 0.866V, or negative 0.779V times V, and that would be our final component there. So I can then say that V vector compared to the initial one, V prime vector, is going to be 0.779V times lambda n, which is the normal vector direction, plus 0.500 V times lambda t, the unit vector in the tangential direction. Or I could, if I did a Pythagorean on these two or found the magnitude of these, I could say that V prime is equal to 0.926V. And I could actually find the angle here by saying by applying the inverse tangent to find the angle, 0.779 over 0.500, or this would be 32.7 degrees. 32.7 degrees. So this is our magnitude, or this is our magnitude and this is our direction, or this is it in rectangular vector form. Okay, so maybe I'll work through one more example, this time looking at the collision of two particles moving in an oblique impact in two directions. This here let's say I have something like this here. So this is going to be an oblique impact of two different masses, each with their own initial velocity. So let's work through this. So consider two spheres or 2-point particles colliding at a point. This is going to be a line of collision. I'm going to construct this. Usually it's good to, when we're doing a problem like this, your first strategy should be to resolve it into normal and tangential components. So if you notice what I'm doing is now this didn't necessarily have to be along this. Initially it could have been something at an angle like this, but what I've done is I have redrawn it and redone the math and run through the trigonometry to find angles relative to the thing here. Relative to the line of impact. So this is the line of impact. And each of these is going to have a mass m. So this is given here. All of this is given. So I have two spheres, each with the same mass. And this one will have a VA of 30 feet per second, and VB here, so they'll have the same mass but different velocities. VB is 40 feet per second. 40 feet per second. And the angles here, well, this one will be an angle of 30 degrees, and this one will be at an angle of 60 degrees. Okay, so all of this is given, and also they're going to collide without friction. And their masses are the same, and also E is going to be equal to 0.9. And so all of this is given, and I wish to find the magnitude and direction of the final velocities of each. Of the final velocities of each. final velocities of each. Okay, so solution. So let me step A here, step 1. 1, resolve the velocities into tangential and normal components. So VA normal is going to be equal to VA cosine theta, VA cosine 30 degrees, which will be equal to 26.0 feet per second. VA tangential will be equal to VA sine of 30 degrees, which will be 15 feet per second. And then VB normal will be equal to negative VB cosine 60. Negative VB cosine 60 degrees is equal to negative 20.0 feet per second. And VB tangential, VB tangential is going to be equal to VB times the sine of 60 degrees equals 34.6 feet per second. All right, then I can apply a few relationships, and basically I'll go through and gain more and more bits of information. So 2, the tangential component of each is going to be conserved. So in other words, so they're going to collide, and each of them has a normal component and a tangential component. So they can exert forces on each other in the normal direction here, along this plane, along this line, but they cannot exert any force along each other in this line. So therefore, the tangential, basically along this direction, the vertical direction is drawn here, their velocities will be unchanged. Each one individually, their velocities will be unchanged. So in other words, V prime A, the tangential component, is going to be equal, so the final one is going to be equal to VA tangential component, and VB prime tangential component is going to be equal to VB tangential component, and this is equal to 15.0 feet per second. So I already know the tangential component of VA prime, and the same one for VB prime. 34.6 feet per second here. So step 3, I apply another relationship, and that is that the total normal component of the momentum of the two-ball system is conserved. All right, so let's see here. MA VA normal component. MA times the mass of A times the normal component of A's initial velocity plus MB VBN, the normal component of ball B's initial velocity, equals, and notice I'm labeling these as separate masses, but and so if these weren't the same mass, you would need to use different we'll be able to replace these both with a single M. So MA V prime A in the normal direction plus mb v prime b in the normal direction. And then I can replace these all with m here. And I can also put in the initial velocities. So m 26 plus m negative 20 is equal to v prime a normal times n, or times m, plus v prime b normal component. This is the normal component. Let me put the m's first because that will be a little bit neater. M times v prime a normal plus m times v prime b normal. Or here, I could divide all the way across by m. So I could also say that if I divide all the way across by m, I get that the normal components of the two final velocities of the following relationship. VA prime n plus VB prime n will simply be equal to 6.0. Will simply be equal to 6.0. And then another relationship I can apply. Oh, we skipped forward a bit. Another relationship I can apply for here is that the normal relative velocities of each are governed by the coefficient of restitution. Of each are governed by the coefficient of restitution. By the coefficient of restitution. So in other words, v prime a minus v prime b, normal component of each, is equal to E, our coefficient of restitution E, not Euler's number, the coefficient of restitution, is equal to VA normal minus VB, but only the normal components of these. These aren't the total velocities, only the normal components therein. So this is equal to 0.9 times 26.0 minus negative 20. So do pay attention to directions here. And that equals 41.4. So in other words, I know that the difference between these two is simply 41.4. So if I solve equations, so step 5, solve equations from 4 and 3, a system of simple linear equations, not that bad. Actually, let me rewrite this so it's very clear. V prime A normal minus V prime B, the normal component, is going to be equal to 41.4. And then finally, part 5 here, I will apply a balance of equations. So solve equations from parts 3 and 4. And 4 together, and we can get that, if you do that, you'll get that V prime A, the normal component, is equal to negative 17.7 feet per second, and that V prime B, the normal component, is equal to 23.7 feet per second here. And so if I were then to summarize all of this, I would get that V prime A is equal to negative 17.7 times lambda t, the tangential component, or the tangential unit vector, plus 15.0 lambda n, the normal, the unit vector in the normal direction. Or I could say, if I want to look at magnitude and direction, I could say V prime A equals 23.2 feet per second, and the theta, by doing an angle, an inverse tangent, is equal to 40.3 degrees. And I could also say that the v prime b is equal to 23.7 times lambda t plus 34.6 times lambda n, unit vector. And then finally, if I wanted to put this in magnitude and direction notation, more of a radial form, it would be 41.9 feet per second at an angle of theta equals 55.6 degrees. And that would be my final answer here. So that will conclude my examples here. I just wanted to work through a couple brief examples to finish up part 3 of this lecture over collisions, impulse, momentum, etc. So that'll do it for today. Thank you for watching, and as always, thank you.